Okay, I'm going to do a review, a little bit of review of what the plots for linear regressions sort of look like. But first, let's recap a little bit of information from regression, since it's a little while ago that we did that. So these are just a basic summary of assumptions that we make when we deal with data that we are intending to use linear regression on. Some of which include the association, basic association of linearity between our predictor, which is our X variable, and the outcome, which is Y. So that's pretty self-explanatory. Other assumptions that we do have to keep in mind when we're doing regression is the normality of the residuals. I'll explain what that means in a second, but basically our error terms are assumed to be normally distributed, right? So we also have this assumption of homogeneity with regards to residuals, and what that means is that our residuals are assumed to have constant variance. We can tell if our residuals have constant variance by looking at a residuals plot. We'll see what that looks like in a second. This phenomenon is also known as homoscedasticity. And last but not least, we also assume that our residuals are independent of one another. Just another quality of those that we have to consider. When we do have these assumptions, we also run into issues. Sometimes our data set doesn't conform as well as we would like to whatever our linear model may be. Sometimes our data is just not linear in nature at all. It might have some other distribution or trend that we will soon notice when we try to plot. Sometimes our information will be heteroscedastic, and that is the opposite of what we need for linear regression. So we'll also see an example of that, but basically our residuals change in variance over time and are not constant. And other things that can influence whether our data set is fit for linear regression is the presence of outliers and certain leverage points in our predictor matrix. And of course, we have tons of diagnostic plots that we can use. We'll go over the most basic of those to sort of parse out this information. The fundamental equation, basically, for simple linear regression, this is what the equation is. We have a very familiar setup here, where our y-intercept is listed, and as well as our coefficient. When our algorithm estimates a line of fit for regression, what it's really estimating are these two beta values here, our coefficient, which is essentially like a slope value, and of course the intercept. So these are the uncertain variables in our equation that we need to figure out. The random error component here is also listed. Keep in mind that this is assumed to be normal with mean 0, and variance sigma squared. So that's what that is. Like I said before, producing a residuals plot, which is essentially just the difference between what our data points are or error terms are and what our model predicts. So essentially normalized to the line, which is 0. It's just the difference of the true value of y and the predicted. And in this case, our error terms are pretty randomly distributed, which is exactly the kind of behavior we want to see here in the first visual. When our residuals change in variance, such as here when they start fanning out towards the end, that's a sign that perhaps we're missing some sort of underlying trend here. And even though the mean is still, the error terms are still roughly distributed across the line evenly, they're obviously changing in variance, and so that is indicative of something we need to pay a little more attention to. And in the last case, which is probably the most common case, is when the data itself is just not linear at all. And we'll go over how to identify that. Yeah, I'll go over the plots for that. So in this is essentially our notebook. We go over a few, well, a little more than a few different packages, but the ones you really need to pay attention to are all down here under sklearn. sklearn is probably one of the most versatile data science packages in Python just because it has access to so many different models. So if you wanted to do like a decision tree on something, you could use sklearn to do that. Same with linear regression, there's a package to that as well. So it's very useful for a variety of different things. If you're interested in the documentation for all these things, I've kept all the links in here. And this actually I'll share after the fact. So you can have that as a reference for later. But basically we simulate for the purposes of this, just a random distribution of points as if we were simulating a real data set and plot it as such. We notice that, you know, just looking at it, you can tell that this is pretty linear in nature. You would probably say this is a relatively linear relationship, okay? The coefficient listed is exactly what our beta 1 coefficient would be, so our slope, essentially. If we're going to try to fit something, it's really quite simple. We take our linear regression method and we'll fit it to our data x and y, which we have defined earlier. And now that linear regression model is saved in our variable name, which is model. Okay, and then we essentially create our line, which is listed here as y predicted by using the predict method on our model object. Okay, we predict with respect to x, which is our training information. And so once we plot that, we can tell that our line does, in fact, seem to fit this information fairly well, just by looking at it. We can also access what the estimated parameters are, which are essentially features of the model object. And we've printed them here. We can tell how well our line fits the data using a simple R-squared score, which is listed here. Right, and that essentially compares our y prediction, which is our line, to the array y, which is our actual data points. Right, so this is our true response. This is what we predicted using our linear regression model. Now, if we wanted to know that this was a good fit for our data, we would want to take a look at our residuals plot. Residuals are a fairly simple calculation. It's just the difference between what we've predicted, so our line, and what each of the individual data points are. And we plot that on a horizontal axis, and we end up with something that looks like this. Now, looking at this, you would probably say with a fair amount of confidence that, oh, this is a pretty normal distribution. Our line does seem to fit fairly well. Our residuals are scattered rather evenly and seem to have a similar number above the line as below. We would wager to say that's a pretty good fit. We can also tell by plotting a histogram of residuals. And as we would expect, it seems to follow a fairly acceptable normal curve. So assuming our data is not necessarily completely linear, like our simulated normal information, say we do a few transformations on our data set, we'll have something that looks a little different like this. Relatively linear still, but there's obviously some sort of correlation here that may cause some issues. And we're going to try the same exact method on it. So despite the fact that our linear regression model does seem to capture the information fairly well, just on the basis of having one coefficient, we're going to notice that the tails here are still showing a little alinear behavior, right? So while it's not super apparent here that maybe your line is not the best model for this information, our residuals plot will tell us that, you know, there is some sort of underlying trend that we need to look at. It's much more apparent here than it would be above. So that's why we plot these things. Notice that our residuals change from left to right as we go. When you see something like that, you would think to yourself, okay, maybe there's some sort of a linear relationship here. Plotting the histogram of the residuals reveals the same kind of concept. You'll notice that our histogram has two different peaks on either side of 0. This sort of clues us into some sort of atypical behavior. So this is just an example of how we would deal with a polynomial sort of thing. If we were to, decide that this is a relatively simple model, maybe we need to make it a little more complex. This is what we would call underfitting to our data. We want to introduce a more complex model. So I wouldn't pay too much attention to this. This is just something that simulates a polynomial equation. So we're essentially adding more coefficients, right? Now, instead of having one estimated parameter like we had before, now we have 25, because that's the degree of the polynomial. So a bit of an extreme example, but we'll notice that our R-score improved a lot, by at least like 5% as compared to what it is before. Keep in mind for R-squared, the closer we are to 0, the more ideal the fit. But yeah, so we'll notice that this is actually a lot better for our particular behavior here. This is an example of what we would call overfitting in most cases if you were to fit this well to your data set. As a good data scientist, you might be a little suspicious because it is, tends to be a sign of overfitting, but we'll talk about what that means later. And last but not least, if we're assessing the normality of our information, like we have a data set, we want to see if it could follow a normal distribution, we would produce something called a QQ plot. And essentially with the QQ plot, you're plotting your sample and your theoretical quantiles to see if your data follows this sort of diagonal line, right? For the most part, this comes from a generated set of data that is from the normal distribution. So obviously, the QQ plot's going to look pretty good. Our tails are relatively close to the line. There's not too much variation. This is an example of a very normal data set. If we had information that came from a different distribution, this would obviously not be the case. Obviously, our sample quantiles are very different than what you would expect for a linear behavior. So in this case, you would know definitively that your information is not following a linear normal distribution, right? So those are just a few different useful functions if you're going to try fitting a linear regression model to some piece of information that you do have. But that is not the end-all be-all of supervised learning. Today I'll go over some of the, and if you are trying to do this in R, included a couple resources here that will be useful for you if you decide to try to do all the same stuff in R. So linear regression is basically a form of supervised machine learning. Among other types, but in general, for our supervised machine learning pipeline, which is what the majority of projects that students do are, there's a pretty simple workflow, right? Assuming we've gone through a process of finding a data set, cleaning it, evaluating it for quality issues, and we're ready to do some sort of experimentation on it, we'll follow these steps in relatively the same order. First thing you're going to want to always do is split your data into a train and test set. And essentially what this means is you're taking your entire data set, say it's like a data frame or something, and you're partitioning it into a section that you are using to train your information, and then a set that you are setting aside. We'll often call this like a leave one out sort of situation, where you leave out part of your data set for testing at the very end. We'll see why that's important in a second, but that's usually the first thing we do. We partition our data set. And we don't touch our data set, our test sample of the data set for the rest of our pipeline until we're ready to evaluate their performance. After that, we'll do our general analysis of stuff. If there's any additional cleaning that needs to be done or transformation, we often do it here. We also do our modeling step here. As you saw recently, using certain packages like sklearn, modeling is fairly easy, and a lot of it is done for you. A lot of the parameter tuning is done for you. So really the setup is the majority of the work when you're doing these sorts of things. Which you do have the power to control are the hyperparameters. We'll talk about what that means exactly. Hyperparameters are different than parameters. That's a little confusing sometimes for people, but there's a pretty distinct difference there. After doing all this modeling, we'll validate, which is another step that's important. Talk about why, and then using these sort of validation tests, if you will, we'll tune our model so that's more efficient, fits better, so that we have the optimal hyperparameters. And then at the very end, we'll bring our test set that we set aside at the beginning back into play, and we'll test our model at the very end and see how well we did. So in terms of supervised learning, there are two distinct types of supervised learning, one of which is regression, and regression's obviously a sort of umbrella term for predicting some sort of continuous quantitative value, right? With linear regression, it's obviously on a linear scale, but there are other types too, exponential, polynomial, all sorts of things, right? Good examples of these kinds of problems are like if you're doing like a housing prices sort of data set, where you're trying to predict housing prices based off of like certain input predictors. That's one thing. Anything that has to do with like revenue or money, stuff like that. Miles per gallon for a car. These are all different things that could be a regression problem. Classification is a little different. In this case, we're predicting a category. So not necessarily a numerical value on a continuous scale, but rather whether there's some piece of information with these certain traits belongs to one category or another. Our Titanic problem is a good example of a classification problem. The categories being whether you died or survived at the very end. A lot of image classification problems fall under this branch of supervised learning. And that's something we are all probably familiar with on some scale. It's this sort of ongoing machine learning problem where you feed an image to an algorithm and it can tell you what object is in the picture. You know, so on a very simple example of this is if you were to like upload like an image of a cat to your algorithm and it could tell you some sort of binary response, it is a cat or it's not, that sort of thing. Or in the more broad sense, identifying a type of species, which could be any number of classifications. These are just other examples of classification problems. A lot of these are actually very common data science projects for students in this club. We've had all sorts of presentations related to these topics specifically in past showcases. So this is just some idea of things that have been done in the past. Again, the real key takeaway for machine learning is that we're trying to figure out relationships between features, right? Sometimes some features will be more important than others, but there's no way of knowing which will be more important until we've done our analysis on it. Almost every model you'll learn about has essentially that same goal, right? So yeah, saying model is a little bit of a, I guess, a vague way of putting it. A model is really just a function, right? Earlier we created a model object, and that's essentially just an equation that produces different outputs depending on your inputs, but has the same general structure. The thing is, we have to actually create the structure of that equation by using existing information. That's where our training data set is really important. So yes, we'll fit our model on our training features and our training labels. So everything that we set aside in our training set, and then we validate by splitting that training data set further into smaller subgroups that we use for cross validation. And this is a process that can be repeated essentially infinitely, depending on how much you want to toy with your model, how much you want to try to improve it. And that's sort of an ongoing process, right? And then once you have validation metrics that are, to you as a data scientist, look pretty good, they seem like they'll work out well, you test it on data that you haven't yet encountered. You'll use your test set. So overfitting, this is just sort of a recap of the plot we created before, but overfitting is something we really have to avoid when we're creating models, because there are in a lot of cases instances when you fit a model to your training set, but it doesn't do a very good job of predicting information that it has not yet seen. So say you train a model on your training set, you try to apply it to your test set, which is completely new information, and it doesn't perform very well. It's because your model is likely overfit to the information that you do have. So it does a really good job of predicting based on the information it has. It doesn't explain new data points that come from the same distribution. So yeah, just because, so essentially having a higher squared score or some other validation method for your training set isn't always better. And that's just precisely because in this example, you may completely miss out on the behavior of your test set. So sometimes a simpler model is better. There's actually a very popular statistical theorem related to this. It's called like Gauss's razor, if you've heard of it. And it's essentially the notion that if you can, having a simple model is always preferable to having a complex model. Just because at the end of the day, another human being is going to have to interpret the results of your model to some degree, and having it be simple is almost always better than having something that's very hard to construe or figure out. So every model has, to some degree, hyperparameters, sometimes more than others, but most of the time these hyperparameters are just like sort of these external variables that use the experimental scientist, the designer of the experiment, things that you can control, right? Common examples are the ratio of the train test split. So like whether you take 80% of your data as your training set and 20% as your test set, that's obviously the percentage ratio that you can change, right? You can control that. For neural networks, which is not really a topic we touch too much in this pipeline, but it's essentially the rate at which the algorithm learns, and that's like an example of a hyperparameter, because that's something you can pretty much go in and change yourself. And for things like decision trees, which we will visit next week, the Titanic data set, it's another thing that we manually decide what is to occur. And an example of what wouldn't be a hyperparameter, which would be a normal parameter, are things like coefficients in our linear regression model. So like beta 1, beta 0, those are just regular parameters. That's something that the model itself uses to determine the output. That's not considered a hyperparameter. That is something else entirely. Okay, so I'm going to try to explain table cross-validation. It's kind of a subject that's a little difficult to get across sometimes, but essentially we've partitioned our data into our training set and our testing set. Our training set is almost always much larger than our testing set, unless we happen to have more information already. But in this case, we'll say that our training set is fairly large compared to our test set. Test set, we'll take it out, leave it aside. Then we split our training data sets into however many groups. That's why we call it K folds, because our training set is split into K number of folds. In this case, this is like 5-fold cross-validation, so we split it into K equals 5 groups. Okay, that's pretty, I would say, a pretty common number for that. The first part of this whole this is a very iterative process, but the first step in that is to take one of the folds and designate that as our validation set. So you can think of this as sort of like a mini test set. So this is a test set that we're going to use at this step of the process. The only thing is each of these folds is at some point in the process going to be its own validation set. And in each iteration of this cross-validation process, we will train our model on the remaining folds other than the validation set. So in this case, we'll take folds 1 through 4, use that information to train our model, and then test it on our validation set, which is new information that it has not seen. We'll record a metric for that one. We'll move on to the next one. We'll train a new model on the other folds that have not yet been used, and test it on our validation set, a new validation set this time. Record that metric, move on, do it again, do it again, do it again. And at this point, we have 5 different metrics now because we validated 5 different times, K number of times, right? And we'll get a pretty good idea of how accurate our model is by taking like the average of all these different accuracy scores and using that as our metric. So yeah, like most other things in data science, there's not really a one size fits all for sort of rule for this. Train test splitting is pretty subjective. It is a hyperparameter that you sort of decide. In general, I would say something like an 80-20 split is pretty ideal for most situations. If you have less data, it might be more beneficial to have a larger test set. So you're not just testing your accuracy at the very end on like 1 or 2 different individual specimens. If you have a lot of data, if you have like millions of entries or something, something like a 90-10 or 95-5 could be even better. Just because you have so much information, and that 5% could still be a very large data set in its own right. So this is something that happens a lot in deep learning. So different metrics, regression, we talked about mean square error, and that's essentially just evaluating how much differences there is between what we predict and what is our actual values. It's a little different for classification. In this case, we have a few different ones that all sort of measure a different aspect of whether or not we've classified something correctly or not. This is a common example of what you would find in like clinical trials when, for example, if you were attempting to measure the accuracy of like a COVID, like a testing kit, like you had a COVID testing kit that was deployed to a lot of different people, and you wanted to evaluate how effective it was at correctly identifying whether or not someone has COVID or not. Again, a binary classification problem. So your precision value, for example, would be the number of true positives, the number of people that the kit correctly identified as being COVID positive over the denominator, which is the sum of both true positives and false positives, which is the number of people that were falsely identified as positive when they were really negative. So that's one metric. Obviously, if there's less of a difference between the smaller value that false positive number is, the more accurate it would be with regards to precision. So that's one way of doing it. And all these are different methods of doing that as well. So deciding between, looking at all these different metrics, there are a couple different rules like of thumb that you can think about. In the case of overfitting, which is when our model is too complex, these are a few things we can do. Gathering more data is always beneficial, but not always feasible in a real life data science application sort of issue. In the case of overfitting, we can also do a little more research into our parameters and see if we can't identify any behaviors just based off of our domain knowledge to make some sort of adjustments that way. And in some cases, maybe our model is just trash and we need to consider a different method altogether. That is not always the answer we want as a data scientist to encounter, but sometimes it is the case that, maybe the model we wanted to use is not optimal for whatever reason, and that's fine too. In the case of underfitting, when our model has no variation at all and it's not really capturing the behavior of even our training set, We'll see what that looks like in the next slide, but there are a couple things that we can do as well. And one of them is possibly increasing the degree of our model. So like before, when simple linear regression was not quite capturing the nature of our polynomial data, we increased the degree of our equation, and that was essentially solving the issue of underfitting. And in some cases, we have good training metrics and good cross-validation metrics. In this case, this is sort of the end goal of this process, which is when we know that our parameters in our set are relatively optimal and we're perhaps ready to test it on our test set, which we left out at the beginning. So this is just one example of what a validation error versus training error graph would look like. In this case, our x-axis is measuring a difference in model complexity. So this specific example would be like having a regression problem where our degree increases from 1 to whatever higher number. And the more coefficients we have, the more complex the model is. You'll see that in the beginning when our model is relatively simple, like it's just a straight line here on the left, we're experiencing a model that has very high bias, and this is a part of what we would call the bias variance trade-off. If our model has high bias, it usually has very low variance, and if it has high variance, it usually has very low bias. And there's a lot of reading that could be done on that, but essentially the takeaway is in our high bias range that we have here, our model is much too simple. All of our predictions are relatively similar to one another. The problem is that they don't have enough variance to capture the behavior of the true function. When our model is too complex, the degree of our regression problem is too high, for example, there's too much variation and there's not enough consistency here. If there were to be more data points added to this, the accuracy would decrease quite a bit, which is why we see that the validation error is so much higher than the training error, right? We overfit to the training set, doesn't do very well with data it hasn't seen before. That's why there's such a difference here. The area we want to be in is exactly what these two boxes do not cross, which is when both our validation error and our training error are low, which means that it's relatively good at predicting both what's already in the training set, what it's seen before, and what it hasn't seen before, which is in our validation. So that's the kind of thing you want to look out for when you're creating sort of these different plots. So yeah, again, I've included all these different like documentation references for different models that we use for regression. So like the documentation for linear regression, which we used earlier, is here. Regression trees are also here as well, which are a regression version of decision trees, which are something we'll go over next week. And there are also different types of regression as well, ridge regression, lasso regression, all sorts of different things. Random forests is essentially an ensemble learning algorithm. It's like a combination of several regression trees, right? And this is just more references for if anyone's interested. Common models for classification. So the reason logistic regression is listed here is that it's sort of a model that represents a binary distribution, like a binary classification problem. Like if someone's COVID positive or not, you could easily generate that sort of a plot using a logistic curve, which is why that's listed there. And decision trees are the classification version of regression trees. Support vector machines are another type of thing. Might talk about that a little more if we have time later in the next coming weeks. But yeah, this is an example of what a classification tree would look like here on the right. And that's, it's a pretty simple diagram because this is something that it's very easily visualized. Yes. if you ever read like an article or something. But yeah, more resources for stuff. Yeah, these are all the links for everything. This is all included in the slides. That's all I have to say today. That was a bit longer than usual, but next week I'll go over, what am I going over next week? I'm going over cross-validation next week. So like all this stuff, I think I included a link to this somewhere here, but basically like tons of cross-validation stuff. And then some decision tree fitting. So we're going to figure out who survives the Titanic or not, based on putting them through a decision tree. So yeah, so that's all I have for this week. Yeah, I'll see you guys all next week.
Is it on the website?
I'll put them in the Slack right now. Yeah.